So using the coffee filter as our starting point for talking about drag. When I first released the coffee filter, what was the velocity of the coffee filter? Can we agree then that it was 0? So I'm going to be kind of esoteric here. At time 0, the velocity of the coffee filter was also 0. Just keeping that up at the top here. This is what I'm calling a boundary condition. And for you guys who have never had calculus before, please understand that is a very important phrase for me. Boundary conditions or initial conditions. They stage our problem and are used later. Generally, understanding the boundary conditions is going to get you a point later in the problem. When I first released the coffee filter, the only force acting on it was gravity. So if I wanted to understand the acceleration of the coffee filter, I could just state, using Newton's second law, that the net force equaled ma. Being that there was only one force acting on the coffee filter, it's not too hard to figure out what the acceleration of the coffee filter must have been at time 0. Right? No big deal here, correct? But the moment the coffee filter started to move, there had to be something that reduced the acceleration, another force that acted on the coffee filter, and we've come to call that force drag. So F with a subscript D, or I'll just write it all out, drag. Drag is actually a complicated force and comes in many varieties. We kind of think of it as the frictional force that occurs when an object has to push the air around itself, out of the way, so it can pass through the air. But drag itself is complicated. It's complicated by many factors. There's more than one kind of drag. There's laminar drag and turbulent drag. And drag is often influenced by the shape of the object. Some shapes can cut through the air better than other shapes can. So when we talk about drag, please understand aerodynamics is complicated. We will look at a simplified version of this. Most generally in my class, there's only 2 forms of drag that are discussed. There's drag that's proportional to the velocity and drag that's proportional to the velocity squared. Today we're going to concentrate on drag that is proportional to the velocity, which means we say that the drag force is equal to C times V. C is just my proportionality constant. It's a meaningless constant that I'm making up to say that the drag is proportional to the velocity. You could argue that this has several things associated with it. The cross-sectional area is probably a part of C. The shape of the coffee filter is probably a part of C. Objects that are smoother and don't disturb the air so much probably have a smaller C. Objects that are bigger or maybe are bulkier or have more right angles to them, they probably have a larger C. I think it was pretty clear from what we just did a moment ago that me crumpling up the one made its C value smaller, and me leaving the other one nice and full made its C value bigger. Does that all make sense? Now, you kind of need to think about this for a minute. And let me just kind of erase all of that and say that our initial condition ended up having an acceleration equal to g at time 0, but a velocity that was 0 at time 0. That's what we understand for the initial conditions of our object. Acceleration means change in velocity. So there was an acceleration acting on the object, clearly, and because of that, the object's velocity changed, and so now the object is moving. Agreed? So when the object is moving, there's now a drag force that acts on the object. That suggests that the acceleration will now be less. Agreed? In fact, how much the acceleration is less depends on how fast the object is going. So the object begins to speed up, but when it speeds up, its acceleration gets smaller. But the acceleration isn't zero, so it speeds up some more, right? But now the acceleration gets smaller, but it's not zero, so it speeds up some more. Eventually, there's going to be the final state of the problem where the drag force will grow to be large enough to equal the weight. Can you imagine that condition? That's what you saw. When I dropped the coffee filter and it was traveling at a constant velocity, that was when the net force had to be zero. We call this the terminal velocity. In fact, it's not hard to figure out what the terminal velocity is. We have all the information we need. We don't know what c is, but we know the other things. In fact, imagine what we did. We did an experiment that proved this to be true. Do you know the experiment we conducted just now? I dropped one coffee filter and then repeated and dropped two coffee filters and compared it to one coffee filter. Did you notice how the one with two coffee filters went faster? Did it look like it was going twice as fast? Because that's what I see here. Now, there's no way to know. We could measure it, but I think it was a pretty straightforward example of what we saw. Now, it also suggests to me that if I crumple it up, I make c smaller. If c is smaller, terminal velocity is greater. Does that also make sense? We're following that so far? We call this, these are the initial conditions, or the time equals zero condition. But this right here, this represents what we call a steady state condition. In the steady state of our problem, we reach a condition where our system is no longer dynamic. There's no acceleration, and the object is simply moving at a constant speed. What we're interested in today is the middle, the transition that occurred. That's where the problem is interesting, and that's where the math is interesting. So although there is the initial condition of the problem and there is the final steady state of the problem, the transition of the problem is where the action is. And that's where the differential equation is. So before we go any further, let me pause this for a minute and stop to tell you a couple of things that I think you need to understand. They're not going to say to you, here's where you have to solve a differential equation. Now, they might use the words differential equation. That is not uncommon for them to say, and I'm quoting what's on many tests, set up but do not solve a differential equation. You will hear that phrase not unlikely on your exam. Set up but do not solve. So there are points given just for setting up the differential equation. Generally, the very next question will be to now solve the differential equation and derive a function. In this example, it would sound like this. Derive a function to find the velocity as a function of time. That's almost a perfect quote from almost any of these particular examples. These problems are always about finding velocity as a function of time. It is the number one example that they use, and they use it every other year. So it's very likely this is what you're going to see. Now, the reason I'm kind of being so beginning, that usually is find an expression for the terminal velocity, which we just did a few moments ago. Our steady state condition showed that the terminal velocity equaled this. They'll usually do that right in the very beginning. And then the very next thing they're going to do is ask you to set up but do not solve a differential equation that could be used to find velocity as a function of time. So that's what I want to train you on how to do. And we'll see if we can do that in the next 22 minutes. First, if you are asked to set up a differential equation, you need a starting point. And they're going to use the word derive, which has the highest threshold of evidence. That's because they want you to start in a specific place. They want you to start with a fundamental property or a fundamental equation, this is where you start. There are only two places in mechanics for us to be able to start a differential equation that have any relevance on what we've been talking about. And here's where they start. Now, it is true, you could have to start here. But this is the most likely. They've never asked one like this. So we're going to start here with Newton's second law. And the reason is simple. And this is where you should put a little asterisk in your notes. A differential equation is any equation with a differential in it. It's not complicated. It's made more complicated than it is. A differential equation is any equation with a differential in it. They're even going to tell you which differential to use. When they say set up or derive a differential equation that could be used to find the velocity as a function of time, they are saying to use dv dt, velocity as a function of time. They're telling you the differential, and that's acceleration. We only have a handful of differentials that we've been taught, and the two most common are dx dt and dv dt. So if they say to find position as a function of time, they're telling you to use a differential of velocity. And if they're telling you velocity as a function of time, they're telling you to use acceleration. So when I said to you guys that you're going to have to set up a differential equation, you need a starting point. You need an equation that has acceleration in it. That's why we start here. It is a fundamental relationship. That's a starting point. And this fundamental relationship already has acceleration in it. This is why you almost always will start with Newton's second law. Now, that's the starting point. We are doing this portion of the board right now, making a differential equation. And it says to start someplace, I'm telling you to start with Newton's law. Now, it's a Newton's law problem, so you're going to have forces that you'll have to put in there. One of those forces is very likely to have velocity in it. That's the whole point. In this case, we have that. We have mg acting downwards and cv acting upwards. Make your directions agree. It accelerates downwards, so I'm making downwards positive. So write out Newton's second law, then sub in the forces that you know are acting. It will be one-dimensional, I promise. It'll be a one-dimensional problem. They're not going to do anything more complex. They're not going to add in angles and stuff just to screw you over. I hope not. They never have. So it's going to be one-dimensional. Now, all you have to do to satisfy the question is substitute. You're done. You have now made a differential equation that could be used to make an expression for velocity as a function of time. That's all they're going to do. And you will probably get 2 to 3 points just for this. Likely 2. 1 point for the net force portion, 1 point for the substitution. But it's that simple. It's no more complicated than that. However, almost immediately after that, they're going to say, now solve the function. And sometimes they'll give you what the solution looks like, and sometimes they won't. Look in your notes. Here's a good place to stop and draw a quick little note to yourself. We're going to show how to solve the differential equation. It's probably going to be worth a total of 3 points. This is after you've set up the differential equation. The solving of a differential equation is probably going to be about 3 points. If they give you the answer, then you can't take more than 3 minutes to do it. So if you can't do what we're about to produce in 3 minutes, you may not want to tackle it. Do what you can, but don't get stuck here. They put this at the beginning of the problem on purpose. Does that make sense? So if you spend 7 minutes here, that's 4 minutes you can't use later in the test that you're going to need. So you've got to strategize here. What we're going to do now has nothing to do with physics. It's math. And we've started this process before. So the first part I've taught you is how to set up a differential equation. What we're doing now is we're going to solve the differential equation. Raise your hand if you're in BC. Okay, you BC folks do this different than I do it. And there's a reason why I want you to do it the way I'm describing in class. It has to do with the fact that in BC, and even in AB, I think, you're taught to do this as an indefinite integral and not set limits. I'm going to teach you to do this as a definite integral and set limits, because 1 point is almost always given for correct setting of limits. And if you're not careful when you do it as an indefinite integral and you don't show your work, they may not perceive that you showed the boundary conditions correctly. Now, for the rest of you who have no idea what I'm talking about, don't worry about it. I'm going to show you what you're supposed to do. All right. This is a process. We've talked about this process before. The steps for this process are right here. And so the first thing you do is you solve for the differential. So we're going to isolate dv dt. And I'm no longer holding your hand for algebra. If you miss a step, you should stop me, but I'm not going to hold your hands. So I divided by m to get the differential by itself. Next, you're supposed to split the differential. Now, the truth is, you don't have to isolate the differential first. I do this purposefully because if I do it this way, it's so clear to the graders. But you could have left it as m dv dt and still separated the differential, and your answer will be just fine. Okay? Your next step, though, is just to multiply both sides by dt. That is splitting the derivative. So when I say, though, to multiply both sides by dt, be careful here. When you split the derivative, like we've done here, we are establishing how we're going to solve the integral portion of our problem. So we're setting up something else here in a minute. Now, once we have split the derivative, which I'm trying to go down my set of steps, multiply both sides by dt, you have to collect terms. And to do this, anything that has a t in it has to be on the same side as the equation as dt, and anything that has a v in it has to be on the same side of the equation as dv. But let me be very over the top for you non-calculus students. You are only going to be multiplying or dividing here. There's no way to add or subtract to make this happen. And that's because we've multiplied both sides by this dt. It's going to be multiplied by all sorts of stuff on the other side. Don't distribute it. Just leave it as a single function. If v's in a portion of it, then v's in the whole thing. And you're going to have to move the whole thing over to the other side. So you don't even have to think about this. Does everybody understand? If the expression here has v in it, the whole expression goes to the other side. And that's very likely what you're going to have. So I'm just going to have dt by itself on this side, and I will have dv over all of this stuff on the other side. Okay so far? All right. Once you've done this, you've collected your terms. I know I'm at the bottom of the screen, but I'm going to scroll it up in just a minute. Your next job is actually pretty easy, but this is the one that's going to get you another point. Okay? So splitting the derivative usually is worth 1 point. Once you split the derivative, draw in your integral symbols. We will integrate both sides. We have to. The next point will be for setting your limits. They're going to explicitly give you a point for setting the limits correctly. The top limit isn't anything you have to think about. On the side with dt, the top limit is t. On the side with dv, the top limit is v. Whatever is on each side, you make those the top limit. So for you guys who want to understand why, we are picking a t that represents some point in time in the future. And we're picking a v that represents some velocity at that time in the future. These are our variables for our expression, and they are the top part of your integral. That's not what gets you the point. It's the bottom limits that get you the point. We have to put in what time is the initial starting point for our problem. We said t equals 0. And we have to put in the velocity of the system at t equals 0, which happened to be 0. Now, in your notes, if you want to have your notes make sense to do a problem like for homework, these are given. They will be given in the problem. They're going to give you the boundary conditions. They're going to tell you how fast it was going when you started watching it. Do everybody understand? So this is given in the problem. They just want to know if you can place it into the problem correctly. But right now, just so you know, if this was all worth 3 points, solving this derivative for the function, we've earned 2 of the 3 points. I'm saying that because once we get here, the next step isn't on the board. The next step is solving this. We have to actually do the derivative. And here's where it's going to get a little spicy. I'm saying this because you may not be able to do the derivative. In either way, you only have a couple minutes to do so. Going from this to v equals something is going to be worth 1 point. You may want to decide now whether you can finish this part of the problem or not in 1 minute. Do you understand what I'm saying? If they gave you the solution, you may not want to go further. Because although I have 7 minutes until the bell rings, I'm not sure I can state each thing that has to happen in those 7 minutes. I'm going to try. I had told you to take out your equation sheet. I'm not going to hold your hand anymore. The left side, you should be able to do the antiderivative and plugging in your limits. You've done it before. If there's no variable there, then it's t to the 0 power. And you do the polynomial rule, and you'll get t evaluated from 0 to 1. I'm sorry, from 0 to t. And that's just going to be t minus 0 or t. So from now on, I'm not going to do all that, okay? You're going to have to get good at that. Everybody follow along about why I'm saying that? Because that's not the fun stuff. The right side, some work. So let's talk about that work. Everybody in calculus understands why I'm saying this is work. Even they know this is a lot because it can't be done directly. This is not matching. What we have is something that looks like this. The integral of 1 over x plus a dx equaled natural log of x plus a. That's what's on the integral table. We have to make this look like that. It's close, but not close enough because there's some number times v. Don't be confused that the integral table has x's in it. The x's over here are the v's over here. Does everybody understand? So don't be confused. X is just a model. In calculus, every variable is x. I mean, ask all those people in A, B, and B, C. It's always x, and they wonder why we're always doing dt over here. So we're going to learn something called U substitution. It's a method to make this look like this. But we're going to do it a little different. Not much different. We're going to do it in a way that will be more helpful for the future. So what I actually am going to do is I'm going to say that I'm going to take all of this and I'm going to sub out all of that. There's a good reason to do it this way. You'll just have to follow along. In U substitution, we're going to try and form a simpler integral by substituting in something that is simpler. So my U substitution starts with me saying I'm going to create a new function, U equals. And I'm going to find something in my expression that I'm going to substitute for. I'm going to substitute for G minus C over M times V. That's what I'm going to substitute in. So that's the first thing I do. I'm going to rewrite this as dv over u. I have substituted in u. The problem is now I can't take the integral of u because it's dv. So I need to substitute in something for dv that has du in it. So the very next step over here is to find du dv. I'm going to take the derivative of both sides with respect to v. Now, I will run out of time, so I'm going to press on with things we've already done in the hopes that you can follow. The derivative of g with respect to v is 0. Right? G is a constant. The derivative of cm over v with respect to v, well, it's the polynomial rule. So I write the cm out here. That's v to the first power. So I bring down the 1, I subtract 1, and I get v to the 0 power, which is just 1. So I get that du dv is going to equal negative c over m. Okay so far? Now I have a way of solving this for dv. That's what you do next. So take the derivative, then solve for dv. I cross multiplied, but I can't handhold you for every piece of algebra, right? So dv now becomes negative m over c du over u. Which, by the way, m over c is a constant. I can take it all the way out front. And now I have something to which I have the integral. The integral of 1 over u with respect to u is the natural log. That's what this was at the beginning, just with a equals 0. So however, be careful. U was just something that we were using as a placeholder, remember? We have to plug back in what u was. That's up here. So that's what I'm going to do next. And I had limits. I haven't done my limits yet. I've got 1 more minute. I'm going to finish it. If you need to leave, quietly do so. If you don't remember how to plug in limits, you plug in the top limit first. And then you subtract and plug in the bottom limit. So that's it. That's all of it. That's all the calculus. Now, here's where you're gonna choke, because v is right here. It's the only place it is. This is an expression for t as a function of v. The problem asked for you to derive a function for v as a function of t. You have to now solve this for v. Isolate v. Do you know how to do that? I think some of you might, but some of you right now are still wondering what the heck the ln is. So I'm going to stop here. I think this is a good place to go, but I also want you to think about something. Right, this is it. This is the full thing, and we're not even done yet. And do you have the time to do this on the exam? That's going to be the big question. All right. What's left for us to do now is to do algebra, but I think there's some problems. And the first is, how many of you know what this is? Okay, so it's a subset, and it's not 100%. And it's okay, because this really does not get taught well in algebra. I think part of the problem is I don't think many of your teachers understand what this is either, and that they're unable to communicate it. It is a bit of an esoteric piece of mathematics, but it's so much a portion of what is what we do in physics that it's appropriate. The one on the left is called the natural log, and the one on the right is the base 10 log. The thing to know about this is that if we make it a function like this, and this is going to become very important in a minute, you can raise both sides of an equation to the same base. So the log function is called the base 10 logarithm, because if I raise both sides to a base of 10, then on the right side, the log and the 10 cancel out, and you get this. So what the logarithm is telling you is the logarithm is the exponent. It is an exponent. It's telling you what exponent you would have to put on 10 to get that number. That's what the logarithm is telling you. The natural log is the same, except that the base is a natural, non-terminating, non-repeating decimal that's been given the letter E, the exponential. So now, most of you were taught this in Algebra 2, but I also know that we have a group of teachers, you guys who have science-minded goals. This is everywhere in science, not just physics. It's everywhere. Now, that sounds like a lot. E is not a big deal. It's like asking you, what is pi? You have an idea of what pi is. I don't know how many decimals, but it's a little bit more than 3. Well, E is a little bit less than 3. 2.7. That's about all you need to know. The fact that it shows up in many places, well, that's a different conversation. And for you guys who are mathematically minded, look it up. Look it up on Wikipedia. And I'm saying that because you'll do a lot of scrolling. It is a long article, them trying to explain what E is. So I'm not even going to try, because I would never do it justice. I'll just let you know that when you study things in science or in the natural world, this number, 2.7, shows up places, a lot of places. So you guys have heard of things like radioactive decay. It shows up in radioactive decay. It explains how long it takes something to decay, or at least it predicts. You've heard of things like exponential growth in things like biology. This number shows up there too. And it shows up here in the way in which an object falls through through the air. It's kind of a bizarre value that just shows up in a lot of places that feel disconnected in nature. So let's go back to this function here. We're going to try and solve for v. So I am not going to assume all of you know how to do this, but what I am saying is that if you do know how to do it, you should be several steps ahead of me the whole time. You should do it. You know how. You don't need me to do this. But the majority of you, let's walk through it. The first thing I want to point out to you guys is that we are subtracting two logarithms. Well, logarithms are exponents. So when you have a positive exponent and a negative exponent, well, the negative exponent goes on the bottom side of a fraction. And the positive exponent goes on the top side of a fraction. So that logarithm up there can be written as g minus c over mv. This is the top. And since this is a negative, this can go on the bottom. It's not factoring. This is a rule for logarithms because logarithms are exponents. They obey the rules for exponents. Now, the reason doing that's important is it's combining our logarithms into a single function. And as you saw a few moments ago, we're able to do things with that function. But I want to get the function by itself. So the next thing I'm going to do is I'm going to multiply by negative c over m. That will get it away from this side and place it on this side. You guys see what I'm doing there? It's multiplying both sides by negative c over m. So I have negative c over m times t equals, now I just have the logarithm function by itself. It did come up in the end of the 7th period. Why is there absolute values in a logarithm? And that's not a misguided question. You can't take the logarithm of a negative number. And because of that, because there is no exponent that will make something negative. So because of that, there's no answer if there's negative inside there. The absolute value bars are misleading because you can't just make whatever's in there positive because you want to. An absolute value suggests you can. I put the absolute value bars there to be nice to your math teacher because the math teachers want you to do that all the time. In physics, you should treat these absolute values different. And I'm speaking to you for, like, as an aside because this is never going to come up in our class until it does. Until they say something like, what are some conditions upon which this will work? Well, one condition is this can't be negative. That's important. That's an important condition. And because there's one thing being subtracted from something else, seems to me like we have a condition there. And if you don't know where that came from, that's okay. Look closely at it. You might. If you look closely at it, g minus c over mv. If you multiply through by m, you get mg minus cv. Is there any way that the drag force could be greater than the weight? Could the drag have pushed the object upwards? Does that make sense? If the object's falling through the air, we're going to level off. We're never going to have a point where suddenly the drag pushes it upwards. And that's what we're trying to say here, that that's a condition. And it's in the problem this way. So don't think too deeply on that. We're trying to focus on procedure. So I'll get back to work here. And I don't know if you know what we're going to do next, but as I said before, we're trying to get v by itself. We would like to get it out of the logarithm. So we're going to raise both sides to the same base. So I'll have e to the minus c over m times t on the left. And when I raise the right side to that base, it cancels with the logarithm, and I get g minus c over mv divided by g. So this is how I isolate the v and get it out from being inside that logarithm. There's a couple things you can do from this point forward. I'm going to show you how I would like to do this because I want the answer to look a certain way. So I'm going to break up this fraction and write it as g over g and all of that over g. That way I can write this as okay, just check my algebra, but my algebra is correct. Make sure you know what I've done with my algebra. I want to isolate v, so I'm going to add it to both sides, and I'm going to move this other term over to the other side. So I'll get c over mg times v equals 1 minus e to the negative c over m times t. Almost done. Still trying to isolate v. So I'll multiply both sides by mg over c. All right, so you guys in E&M, it looks familiar because we get this all the time in E&M. Well, twice, but it is all the time. Yeah. No, you're going to get the same thing. So you could have multiplied by g earlier and gotten it out from under that. Would have worked out fine. Yeah, I want it collected like this because there's some things about this that are important. And this is generally what it will look like when they say, show that the solution looks like this. This is the standard form of this relationship. I'm not going to mince words here. Most of you don't know what this is, but a few of you do. This is not exponential growth. This is asymptotic growth, meaning this equation approaches a value. Now, to understand that, let's kind of focus. This, by the way, this is the culmination. This is the end. This is what the term looks like. This is the motion equation for an object dropped through the air with drag. Okay, that's what this is. It's every bit a motion equation. And I'm saying that to you because it works the same way all other motion equations do. Meaning if I want the acceleration, well, that's dv dt. I can take the derivative of this and get the acceleration. But also, this is dx dt. Once you have one motion equation, you can find the others. Now, you guys not in calculus, I'm going to expect you to do this one. We're going to do it today, maybe. This one, you calculus folks, give her a try. She's a little bit more fun. And we're going to do a lab tomorrow to prove what this looks like. So let's start by just kind of examining this exponential function. And an exponential function is just that. It's a function that has an exponential in it. This one has an exponential in it. I want you to understand this. So stop looking at all the letters and look at it a piece at a time. Everything in here is a unitless quantity. Okay? E doesn't have units, so e to an exponent cannot have units. Look at this for just a minute. Okay? This is actually 1 over e to the c over m times t, right? A negative exponent shifts to the bottom of a fraction, correct? Now, remember our boundary condition. At t equals 0, what is e to the 0 power? 1. So when t equals 0, this is 1. What is 1 divided by 1? And that means that all of this is 1 when t equals 0. So what is 1 minus 1? So at t equals 0, v has to equal 0. Now, I know that sounds like, yeah, I know, you said this yesterday. Our equation has to prove that, which means that when you do the work, the first thing you should do is check your boundary condition. It'll tell you whether your algebra is right or not. They'll tell you whether you screwed up the calculus. So put in your boundary condition and see if the boundary condition comes out. That's called the initial state. You should always check two states, the initial state and what we call the steady state. The steady state of an exponential is what happens at the other end of that spectrum. What happens when t goes to infinity? Now, I know in your math class you never have infinity. In physics, we have infinity all the time because infinity in physics might not be as long as you think. So when we say when time is infinity, well, oftentimes that's milliseconds. Things happen fast in nature. So infinity means different things than probably what you've been taught. T just means a really big number. I'm sorry, infinity just means a really big number. So what happens when t becomes really big and it's in the exponent of a number? Silence. I love it. Well, what would e to a really big number be? It would be really big. And what's 1 divided by a really big number? Really small, practically 0. So when t goes to infinity, this term goes to 0. Correct? You follow that? 1 minus 0 is? So v equals mg over c. Now, that shouldn't be a surprise. What did we say the terminal velocity was yesterday? So we said that this thing would approach and reach a terminal velocity. Our equation predicts that. It has to. That's what our equation was supposed to do. It was supposed to figure out what happened in the middle. So it has to definitely have the beginning and the final state we expected, but this now tells us what the graph looks like. What is it actually doing in the middle? And here's where you're usually going to have to do this on the exam. It doesn't matter that you have this equation. You're unlikely to ever actually plug something into this equation. There are features about it, clearly, but it's about it being an exponential and not just any exponential. This is known as an asymptotic growth function, as I said at the beginning. And we now know things about it as an asymptotic growth function. Remember, you're supposed to be able to sketch graphs based on things you have kind of looked at. We know that at time 0, the object's velocity is 0. And we know that after a very long time, the object's velocity is going to be that. So 2 dots. This is supposed to fill in the blank. Now, you should, on your own, grab your calculator or Desmos or something and plug this in. When I say plug it in, you don't have to do the whole thing. Just do y equals 1 minus e to the negative x and see what it looks like. Now's not the time to do it, but later will be. Because what you're going to get is asymptotic. I keep using that word because I want you to get used to hearing it if you haven't heard it before. But an asymptote is a function, or is a something that a function approaches. In this case, the asymptote is mg over c. And this is a function that approaches an asymptote. This is what the behavior of the curve looks like. You should prove that it does, but it has a clear exponential in it. Now, I want you to have followed this. I don't know if you have, but the best way to follow this is to do it on your own a couple times. Your homework has this in a bunch of different mixed cases. But problem number 1 is this, all the way from the very beginning. And when I say all the way from the very beginning, I purposely did it like this, because all the way from the very beginning is a lot. There's a lot of parts here. From the initial part where we just started to deal with the net force, to having to put together our differential equation and splitting our derivative, and then doing a whole bunch of algebra. And that's what all this is. And I don't know, can you do all that in 3 minutes? I don't know. But if you've done it 5, 6, 8 times, and it's the same every single time, well, you might be able to. At the same time, you can still ask yourself, is it worth the 3 points? It may not be. But I believe in you guys knowing things, and this is important to me, that you know things. One more thing before I go on. This is an asymptotic relationship, which means it approaches some function, but never reaches it. That's actually not particularly true. It reaches it. It gets so close that you can't be measurably different. And how long this takes is based on this fraction. That's the fraction that is controlling this. And if you know anything about that, if m, which is in the denominator there, were to get bigger, then it would take longer for this function to reach the asymptote, because I'm dividing it by a bigger number. I'm dividing the time by a bigger number. But that's what happened too. When we doubled the mass of the filters, it took longer to get to its maximum speed, because its maximum speed was faster and drag affected it less. Of course, the opposite's true. If c gets bigger, then the object is more affected by drag. It will reach the terminal velocity sooner. All of that is right there in that function. It controls the rate of the growth. Now, I know I have 5 minutes left, but the last thing I would really like you guys to see is how to get the acceleration from this. And I know it's a hard ask because you guys are looking tired. I can see it in your eyes. But I want to take the derivative. And I want to do so because most of you will probably pick this up pretty quick. If I take the derivative of this, I get a function for the acceleration. Acceleration is a function of time. And this isn't too hard to do. So let's give it a try. First, I'll point out something that I've told you before. It's been a while, but I've told you. The derivative function can be distributed, meaning I can distribute it. Now, taking the derivative of a constant, I can just pull the constant out. So I can write this as mg over c times the derivative of this thing. Again, I can still distribute, which means I can distribute the derivative inside those parentheses. Now, the left side here, that's the derivative of a constant with respect to time. Does a constant change with respect to time? It does not. So the derivative of 1 is 0. But now I have to take the derivative of the exponential. And I know you guys don't know how to do it. Never done it before, unless you're in calculus. Of course, so I'm just using what was on the derivative table, plugged it in there, and did what it told me to do. Now, there's a lot there, truthfully. It's called the chain rule. You should learn the chain rule, and someday we will, but not today. We can clean this up, can't we? Cleaning it up, negative times negative is positive. Cancel the m's, cancel the c's. That's it. Think it through. I've got 1 minute. At t equals 0, what is e to the 0 power? 1. So at t equals 0, a equals g. Well, of course, there was no velocity at t equals 0, so there was no drag. The acceleration was g. When t approaches a really big number, what is e to a negative really big number? Very, very small. Nearly 0. This function is a straight exponential. This function is a straight exponential decay starting at g. Straight decay to 0. All right. It's a whole lot. So here we have a problem that clearly has the possibility of terminal speed, the possibility of setting up a differential equation, but it's one in which the drag force is proportional to v squared. But it's clearly a coffee filter question to be. This is 2013, and this is the same problem. And you'll notice question B, write but do not solve a differential equation. In this case, the object is experiencing some other force, Fa, and it already has a velocity, which means at time 0, it's already moving. But it's experiencing a drag force of magnitude kV. They changed it up there, not C, but kV. Will you be thrown off? Probably. Yes? No, they don't. Sometimes it's far more hidden than that. So although I'm trying to be very overt, that's what I'm trying to show you. These are from 2010, 2013, relatively recent. But I'm about to show you 2019, too, to give you an idea that they sometimes hide it more than this. Oliver? Potentially you could, but they're going to ask for a more explicit derivation. So even though you might be able to do so, you will still have to demonstrate it mathematically. Or not, as I'll explain in just a minute. An integral that will match what you have to do on your exam. So if they're asking for an integral, it's going to be here. And in fact, the integral that we have to do is sitting here on the table. This is the integral we will have to do. So it's on the integral table. And that's because they put this one on the exam. So if you're going to be asked to do an integral, it's probably going to be here. This table changes year to year, depending on what's on the exam. But generally, this is the only one you need to know. This and cosine and sine. So we'll get cosine and sine next week. So I'm actually a bit ashamed about this because I think my students were completely unable to solve this question. It dropped they weren't even nice. An object falling vertically through a fluid in a glass cylinder. I think all of my students kind of flipped out at the idea of this question. But the thing that told them that this was the same problem as the others was this graph. They didn't realize it, but and you're going to see this soon, well, tomorrow, that this is the graph that you will get for an object that is falling through a fluid. It's just a drag example. They shrouded it in this object falling through water or a fluid. But what the students failed to connect is air is a fluid. They behave the same. You tend to think of fluids as liquids, but that's not the word they use. They use the word fluid on purpose. Drag acts the same in any fluid. So gases and liquids are going to be the same. This was just a C times V problem. And that's what in the next portion of the problem it ends up being. But the students saw the liquid, and again, they hid it. They hid this problem, or hid the idea of a differential equation in this problem. What we're going to have to do is twofold. First, you have to get the math, but you also have to know when they're hiding it from you. Generally, they're going to say, find an expression for the velocity as a function of time. You're going to see that in the problem. Yes, sir.